Whenever you read the news and you see the headline that 20% of people in the UK do this, or 40% of the people own this particular thing, and so on, if you ever wonder how they came up with those statistics in the first place, well, they didn't ask every single person in the UK to fill out a survey. Instead, what they did is they took a sample, and based on that sample, they tried to make an accurate prediction. And the way they do that is using confidence intervals. So that's exactly what a confidence interval does. It gives us quite an accurate estimation on what the true mean of a population is for a given property. And the reason why we can do this is based on the central limit theorem. The central limit theorem, although fundamental to all the statistics, it's very difficult to actually understand what is going on and why it works. But in a nutshell, it's this. If the original distribution is not normally distributed, then the sample means will be normally distributed, provided that the sample size is greater than or equal to 30. And in this case, the standard deviation actually changes. It's sigma over root n. Now, if that's difficult to understand, let's have a look at a flow diagram. So think of it this way. You take a parent population, a distribution of some sort, and you think, is it normally distributed? Well, if it is normally distributed, you don't need the central limit theorem. If it's not normally distributed, or you don't know if it's normally distributed, then the next point is the sample size greater than or equal to 30? If it is, then the central limit theorem tells you that the sample means will be normally distributed. It's important to reference that this is the sample means. It's got nothing to do with the original distribution. It doesn't mean that the original distribution is normally distributed. It simply means that the sample means of that distribution will be normally distributed. If the sample size is less than 30, then we can't assume that the central limit theorem applies. Now, what it's worth referencing here is, for this particular examination, we tend to say the sample size has to be greater than or equal to 30. If you look at other publications, sometimes they say the sample size is greater than or equal to 25, greater than or equal to 50, and so on. It's just because the bigger the sample size, the more accurate it is. Let's have a look at some examples on where this is going. So we have a look at this one here, and I'm interested in part 3, and it says state why use of the central limit theorem is not required in answering part AI. Now, the reason why we didn't need a central limit theorem for this question is, as we can see highlighted here, we're told in the question that it's a normal random variable, i.e. it's normally distributed. And because it's already normally distributed, we don't need to use the central limit theorem. On the second example here, part C again, state with justification whether you made use of the central limit theorem in constructing the confidence interval in part A. Now, if we have a look here, it does not mention any reference to it being normally distributed. And our sample size is 36, which meets the criteria of being larger than 30. So based on this, we did need the central limit theorem, because we don't know what the original distribution was. The parent population distribution was unknown. So the central limit theorem was used. And finally, on this one, it says part BI, indicate why the mean annual salary of a random sample of 50 full-time university employees may be assumed to be normally distributed. Now again, if we go back up, nowhere in the question does it say that it's normally distributed, but it does tell us that it's a random sample of 50 people. And if we just look at part BI again, it's talking about the sample mean. And because of the central limit theorem, we know that the sample means will be normally distributed provided the sample size is greater than 30, which is clearly satisfied in this question. Let's see how to use our calculator for a confidence interval. So what we're going to do is we're going to go to Stat, number 2, and on the main menu here, it's going to be a distribution, and we're dealing with a normal distribution for our confidence intervals. So we can normal distribution, and then it's going to be inverse normal. And then suppose we want a 98% confidence interval, then our tail is always centered for our CI, and the area is going to be 0.98. So we execute. We need to make sure that our sigma and our mu are 1 and 0 respectively. We press execute, and we get minus 2.32 and positive 2.32. So these will be our Z values that we're going to substitute into the formula. Suppose instead you want a 99% confidence interval, then you're going to put 0.99 here, and you'll get different values of Z. If you want a 90%, 0.9, and so on. Let's see how to construct a confidence interval. Now the first thing is the formula for it. This is given as mu is equal to x bar plus or minus z times by sigma over root n, and this isn't given to you in the formula booklet. Now this is just a rearranged version of the formula z is equal to x bar minus mu over sigma over root n. But you're going to have to do this every examination, so it's worth remembering because it'll save a lot of time. Let's dive into a question and see exactly how this works. So we can see here it's asking us to construct a 98% confidence interval. Now the first thing we do is we go to our calculator and we work out the z values corresponding to a 98% CI. In this case we're going to end up with z is equal to plus or minus 2.326. If we read the question in more depth, we can see that it tells us the sample mean, x bar, is 118. It tells us the standard deviation is 65 and the sample size is 80. So plugging all this in, we get two values of mu out. We get mu is 101 and mu is 135. Now it's really important to realise that this doesn't mean that the mean is 101 or it's 135. No, these values are representing the lower bound and upper bound of our confidence interval. That is, we are 98% confident that the true value of mu lies somewhere between 101 and 135, and we should probably present it in this manner. In this section we're going to have a look at evaluating claims, and for all these parts we're going to assume that we've already worked out our confidence interval and we've got values that mu must lie between. Now let's have a look at part BI here, and it's saying hence comment on a claim that mu is 140. Now earlier on we worked out that mu has to lie somewhere between 101 and 135. We are 98% confident of this. And now 140 lies outside our interval. So we're going to reject this because our data does not back it up. And we need to make a clear comparison of that. So in the examination, make a comment saying that it lies outside our CI. In the second example here, we would have worked out our confidence interval as mu lying between 5.02 and 5.08. And in the question saying it's claimed that the mean exceeds 5 litres. Now our CI exceeds 5 litres as well. So clearly we're going to accept this because our entire confidence interval lies above 5 litres. So the first claim we accept. In the next part it says fewer than 10% of such bottles contain less than 5 litres. Now quite often the second claim wants you to refer to the actual numerical data. And if we read this question, it tells us that exactly 8 of the 36 bottles contain less than 5 litres. Now 8 over 36 is clearly greater than 10%. So we're going to reject this second claim. In this example here, we would have constructed a 99% confidence interval, and we've got mu lying somewhere between 302.3 and 306.9. And it's saying here, comment with justification each of the following two claims. The first of which, the mean weight of dry cat food in a pouch is more than 300 grams. Now very similar to the previous question, our CI clearly lies entirely above 300 grams, so we're going to accept it. Our data backs this up. On claim 2, it says all pouches contain more than 300 grams of dry cat food. Now in this case, if we have a look at the X bar and we look at the standard deviation, if we do X bar take away one standard deviation, we're going to get an answer less than 300. And as this is going to be a normal distribution, that means there's going to be some parts of the graph that lie less than 300, i.e. some values of data are going to be less than 300. So clearly this doesn't back up their claim that all the values, all of the pouches contain more than 300 grams. So we reject this claim. So the important points to remember for your confidence intervals and your central limit theorem. And the first of which is the formula itself. This will save a lot of time in the examination. That is mu is equal to x bar plus or minus z times by sigma over the square root of m. The second thing is the definition of a central limit theorem. Now although you won't be asked to quote the definition, certainly understanding it is key to answering some of the questions. If you are unsure about this, I encourage you to go back in the video and have a look back over it. The third part is evaluating claims. Now again, we went over this earlier in the video, so go back if you're unsure, but quite often you'll be asked two claims, one of which will be asking you to reference your confidence interval, and the other, the actual numerical values that it gave in the first place. And the final thing is to remember that your confidence intervals are never perfect. If you make a 99% confidence interval, then you can expect your inequality to not contain a true mean 1% of the time. So although we can accept and reject claims, we can never outright guarantee that they're wrong or guarantee that they're right.